Yes, honey.
What do you mean fried when it's getting baked?
Uh, well, I was gonna give you a turkey to graph. Did you, did you want to do stats? Because I was gonna
No.
practice graphing with the turkey. Okay, I mean, I could come up with something else. Okay, anyway, I was actually holding that day just in case somebody was absent for the test and then they could take it that day. That was my plan. That was my plan Z. Anyway, okay. We turn to the park ranger and his trees. Now he wants to find the probability that he will find the first diseased tree on the fifth child. And I underlined first because that's the most important thing here. Um, so I have a question. First of all, do you remember this word from Math 1? It has to do with a sequence, geometric sequence, where, no, okay, thanks for throwing stuff out there, but it's repeated multiplication by the same number. So if it's like times 2 times 2 times 2 times 2 times 2, that was called geometric. And that has to do with, that will help you remember what to do here. Okay, there are 4 requirements for a geometric distribution. They're almost exactly the same as binomial, but there's one difference. Okay, so first, you need to have a success or failure. Does that sound familiar? Right. And in this case, it's diseased or not diseased. So success or failure situation is the same for geometric as it is binomial. They're both the same. Okay. Independence. Still wildly important. You guys remember what we learned last week, though, how you can get around the independence condition? Yeah. Only take out less than 10% of the population for your sample. Then you can kind of cheat on the independence condition. But this time it tells you there's no pattern to the infections. So that way you can get independence from that statement. Okay. There's another thing that's the same probability for each trial. Do you remember what it is for the tree situation? Yep. Okay, and this is now where they're going to differ, where geometric and binomial are going to differ. On binomial, you have a fixed number of trials. And on geometric, you do not have a fixed number of trials. You're looking for the first success. And so I'm going to underline this word first. This is going to be your clue when you're reading a question that you're working in geometric and not binomial. In geometric, they're only going to give you 2 things. And in binomial, they give you 3. So you're only going to have 2 numbers to put in. In this case, we're just looking for first success on the 5th trial. It says 5th right there, so I write x equals 5. Okay, did anybody see my Google Classroom post today? I mean, you might not have read the whole thing, but I put the test topics up early just so that everyone can get ahead because I know there's a lot going on right now. I noted that in one of the test topics, I said proper random variable notation. And I thought to myself, maybe I haven't said that enough times. Proper random variable notation is when you write the P and then X equals or X is greater than or whatever. That's this first part that we write. So in this case, he wants to find the probability he'll find the first disease tree on the 5th trial, exactly the 5th trial. This is proper random variable notation, meaning you have the probability and then you have X equals, or X is less than, or greater than, or do you want me to put that underneath the document, Cameron? You do want me to put that underneath the document, Cameron? No. Are you guys all right? Okay, so the pre-calc way is going to feel like common sense. So let's just write it and then see if it makes sense to you. And I don't really know how else I would write this, but this is first success on the fifth trial. So fail, 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 success. Does that make sense? No other way to write this, basically. Fail, 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 success. And if you like this, you can do that that way every single time. You don't have to do the stats way. Are you guys okay with me just stealing my calculations from previous? Okay, so now we're going to do it the stats way, but we're going to do this one actually in the calculator. So probability x equals 5. This is your proper random variable notation again. And find this guy in the calculator, geometric probability density function, GeoMet PDF. And he is located right by the binomials, but even easier to scroll up. So this is what I do because I'm the laziest human being ever. I go second, vars, up, up. Because I'm just too lazy to scroll down all that way. Okay, now let's take a look at what they're asking for. They only want two values. They want your probability of success and the first success. I want that to be a 5. I don't know why I didn't write 5. I was going to write X because it says X value. I really wanted that to be a 5 though. And then I'm going to label it. Now, what should this answer be? Yeah, 0.080. Okay, now PDF and CDF work exactly the same way as binomial. So PDF is for your equals, CDF is for all of your inequalities, which we're going to do next. Hey, Bryce, can you do me a favor? And can you do uh try the geomets in the thing? Okay. Okay. Find the probability that he'll find the first disease treat on or before the fifth child. So first thing we do is translate to proper random variable notation. On or before is X is less than or equal to 5. On or before the fifth child. Okay, that is your regular CDF. CDF is always less than or equal to. So can you hold on to it for me so I can you tell the shape from it? Excellent. Can I see that in a minute? Okay. Okay, anyway. Do geomet CDA 0.165, 0.582. Okay, that was weird. All right, next. After the fifth trial. Okay, translate that for me. What is it? Probability X is more than 5? Okay, now wouldn't that not be the exact opposite of less than or equal to? That would be the complement, correct? Mm-hmm. Okay, I want you guys to look back in your binomial notes and tell me what to do for greater than or equal to. What do I do for greater than or equal to? What's the thing? You do both things, right? So you do 1 minus, and then 4. Does that make sense? And that is 0.498. Okay, so I highly suggest when you're making your note card, put up a little thing that says binom PDF is equals, and then put up a little, or geomet PDF, just put PDF is equals, and then put CDF is less than or equal to, and then 1 minus CDF is greater than, you know what I'm saying? Do, like, write down all 4 inequalities and make sure that you say what each one of them does. I would suggest highly. Everybody got that? Sure. Okay. Just say. Okay. Now here's the part where I need Bryce's calculator. Okay. There's very good news about some of this stuff. It's just formulas, which is great. I don't know about you, but I like formulas. Easy. But I do want to prove it to you using Bryce's calculator that the shape is always the same. So we just put this, I didn't do any of this. He just put this in. And so these are the PDFs here, and these are the CDFs. And can you tell that it peaks out right about here? Okay, and so what side would it be skewed then? I like to think of it this way. So if I turn my calculator this way, I can think of these as bars. And this is the highest bar, right? So then my tail would be over here, so it'd be right skewed. All geometrics are right skewed. There's no thought process. You don't have to do a formula to prove it's normal. It's not going to be. Yep. It's amazing. It's the best thing ever.
will always multiply by a decimal, so.
Exactly. You're always gonna multiply by a decimal, so you're gonna be getting smaller and smaller and smaller because they're probabilities, so they have to do that. Thank you so much. So we don't have to do any formula to show it's normal. We don't have to do any binom PDFs, none of that. Right skew, done. Okay, the center also has a formula. It's just a wonderful, wonderful formula. Okay, so write it down and then a couple of things. We're going to talk about why this formula makes sense, but also we're going to talk about these symbols. So this says the mean of X. I want you to think of that as the weighted average equals the expected value. You guys have to start reminding yourself that weighted average and expected value are the same thing, interchangeable at all times. If I ask for weighted average, you give me 1 over P. If I ask for expected value, you give me 1 over P. Okay, now why is it 1 over P? Well, let's pretend that Mrs. Talbot is buying boxes of Count Chocula. Okay, pretend that there's figurines of the scary figures in the Count Chocula boxes. And let's pretend that there's 4 different figurines. Like say, I don't know, Count Chocula and Blueberry and Frankenberry and the other one that escapes me. Anyway, probably something transparent. That's my joke. Okay, so how many boxes of Count Chocula would you expect me to have to buy until I got the figurine I want? If there's 4 different figurines, 4. Okay, so this is say 1 over 1/4 of the probability is 4. Yeah, okay, so for the tree situation. Okay, what is this value saying? Does anybody know what the 6.25 is?
The big value.
Of what? Yes, of what?
Of,
Of what?
so we find
What is it? What am I finding in this one?
these.
So on average, you would expect to find your
One in
first
At
disease
this
tree
point.
at 6.25 trees. Yeah, trees. In this case, trees. Okay, so geometric, remember it means first. So you're expecting to find your first disease tree at about 6.25 trees in. Notice that this is not a possible answer because it's over time. You just got to let that go. Yeah. Okay. Now spread. Different formula for standard deviation. You know what I really like about these formulas? They only have 1 letter in them. Good. Okay, so standard deviation. Okay, what does this mean? Okay, let's reword that. So, over many, many trials, you can expect that the first disease tree you find will typically vary between 5.728 trees from the mean of 6.25 trees. Meaning you can expect to find your first of these trees somewhere between 1 and 12 trees in, typically. I think that 5.728 is a very large standard deviation for this. It means that it's wildly all over the place. You could find it on the first one and not be surprised. You could find it on the 12th one and not be surprised. But typically, you're gonna find them about 6 in. So remember that phrase typically varies from the mean. Remember that?
Yes.
Phrase? Okay. Flip in my notebook. Afternoon time. It's way better for you, but not as delicious. You can't put as many wonderful things in it. It's true. Oh, thank you for that. Jamie Balter's done writing. All right, you guys ready? No? Okay. Suppose you roll a fair six-sided dice until you get doubles. Let t equals the number of rolls it takes. Show that t is a geometric random variable. Well, he's across the hall and he likes football. Oh, not that t. Oh, oh, I'm funny. Okay. Oh, it's in my mug. Oh, okay. Trying to be funny. Okay. All right. So success or failure. Doubles or not doubles, right? Okay. Okay. Are rolls of dice independent?
Yeah.
Yes. And if you're like sitting there like, why is everybody so confident about that? It's because when you roll a dice and then you roll it again, all of your options are still open no matter what you rolled before. Okay. Is the probability of success the same each time?
Yeah.
Yeah. And do you know what the probability of success is in this case? 1/6. Okay. If you need me to prove it to you, I'm doing it. It's happening. Okay. So there were 36 outcomes. 1, 2, 3, 4, 5, 6 of them were doubles. Did you hear me? Okay, 36 possible outcomes. 6 of them were doubles. So 6 out of 36 reduces to 1/6. It's not the 1/6 like rolling a 1. Do you want me to put 6 out of 36? Would that make you feel better? Okay, I'll just put 6 out of 36. Okay. So where am I? And do you know where I got those 6 from? Like down the middle column of that table we made? Okay, and then what would a first success look like? First doubles, yeah. Okay, so check geometric. Find and interpret probability t equals 3. Okay, so proper random variable notation, probability t equals 3. Geomet, is it PDF or CDF? PDF. Yep, because it's exactly 3. So PDF with the equals. Nice job. Okay, and we have 1/6, comma 3. This is P and X. And you can type fractions into PDF. That's fine. It's no biggie. Just type it like that. 1 divided by 6. 0.116. Everybody understand that means your first doubles? I underlined it again, really trying to put that first thing in your mind to be geometric. Okay, find the probability that t is less than 3 or that t is a sideways heart. Okay, look back at your binomial notes. What do I do for less than? Okay, first of it, is it geometric CDF or PDF? Okay, and then what? Two. Just a quick note, when you guys are doing your little note card bit, just put like x minus 1. So whatever this is, put like an x there, then put x minus 1 right there. Or put like a put like a M there or something, like any letter you like, whatever your favorite letter is, and then put that minus 1 right there, just for formula's sake. Okay, can you guys trust me on the calculations? Okay, last bit. Describe the distribution and interpret. So fun. Okay, so we need to do 3 things to describe. Yeah, we don't have to interpret that either. Just shapes, right, skewed, done, check it off. Okay, center. Okay, now if you took me And for any other math class besides this, you're going to recognize me saying keep, change, flip. This is a keep, change, flip situation to 6. So keep the 1, change to times, flip to 6/1. So 1 times 6/1 is 6. Yeah. Keep, change, flip. Few years ago, there was this like thing through the math books where they wouldn't say the word dice for some reason. They thought that was like a derogatory word. So they called them number cubes. I don't know why. I find that so funny. No, it wasn't that. It's just that they thought it was just like a bad word, like a guys are being so rude right in front of me. So this, if you're going to do this in calculator in one swoop, would require some parentheses. So square root 1 minus 1/6, that's not a big deal. Oh no. Gotta not delete it though. Divided by, and then make sure to put the 1/6 in the denominator in parentheses if you want to do this in one motion in the calculator. Or you could just do times 6. You could just do the top thing times 6 either way. Or you could do the top thing and then hit enter and then divided by 1/6 and then hit enter. But if you want to do it in one swoop, you need parentheses. Maybe this would be better. Square root 1 minus 1/6, enter, divided by, no, it's still going to be, I don't think I got out of it in any way, shape, or form there. Anyway, use parentheses. Okay, sentence. this is another really big standard deviation. Like it's almost pointless, really. Because you don't even know if you're gonna get doubles anywhere from 1 roll to 12 rolls. A lot of variation there. Seems like a, I don't know, maybe a volatile gamble. Just throwing that out there for my friends. Okay. So finish up this, and then I want to show you your joke. And it's the last slide of chapter 6. Okay. What happened? Oh, I'm sorry. That's terrible. Public school furniture. Okay, here we go. Okay, let's see. Did we calculate and interpret probabilities involving geometric random variables? And calculate, interpret the mean and standard deviation of a geometric distribution? Okay, there is the homework, and there is your joke.
Okay.
What?
Probability are. I was gonna tell her that the most. Whatever. That's what really. Now is the best time.
Have to write it, the equals expected.
No.
You just do it just to
It's
show
really
it's the
just,
same.
I'm just doing it repeatedly over and over and over again
Okay.
because people are like, what's expected value? And I just want to have it in there a million times.
Yeah.